Okay, welcome to another flip session of chemistry today. Today we're going to be talking about weighted averages. Okay, we're going to be looking at how do I calculate average atomic mass. So working with weighted averages. Okay. So the high school where I teach, the way that grades are calculated is there's 4 terms. Each term is 20% of the student's grade weighted, and then the mid-year exam, MYE, is 10%, and the FYE, the final year exam, is also 10%. So the terms weigh heavier than the final and mid-year exams. Okay? So, for example, if we try to calculate someone's chemistry grade, not using weighted averages, what we would simply do is we would add up the 85, the 88, 79, 86, 70, and 89, how they scored in each term, plus how they scored on their test, and divide it by 6, because there's 6 items. So if we do that now, just to show you the difference between average and weighted average, you're going to need a calculator for today's flip session. So 85 plus 88 plus 79 plus 86. Please check me at home and get the right answer here. Plus 89. I get 497. I get 497. Divided by 6. This person's going to get an 82.8%. So this person's looking at a B minus grade, okay, without weighted averages. Okay? But if we take a look at this student, okay, with weighted averages, it's going to be a little bit different, right? So if each term is 20%, we're going to take 20% of 85. So 85 times 0.2, that's going to give me 17 points. 88 times 0.20. Because remember, I'm multiplying by the weight, 20%. Okay? So 88 times 0.20 gives me 17.6 points. So these are the points that are building up to that student's average, how he or she will do for the year. 79 times 0.20. That's 15.8 points. And finally, 86 times 0.20 is 17.2. Excuse me, 86 times the weighted average, 0.20, equals 17.2. Okay, so we're going to start to add up these scores. Okay, now the exams here, the exams are each 10%, so they're less heavy than the terms. So to get 10% of a number, we multiply it by 0.10, and we simply move the decimal over. So that's going to be 7 points. And 89 times 0.10 is 8.9. Okay? So we have what each term in year exam contributes to the average. I'm going to add up these scores here, 17, 17.6, and that's going to give me the student's average on a weighted scale. Okay, it's going to be an 83.5. So this person has a B, and this person has a B minus. Now they're close, okay? And that's because the weights are pretty close to each other, 20% and 10%. But if these were skewed, if your terms were, let's say, 10 each, and these were more than 10%, it would be skewed more towards the year exams. Okay, so that's how you're going to calculate using weighted averages. A little bit different than regular averages, actually much different. All right, so using the same concept, how do we apply this weighted average to isotopes? Isotopes come in different abundances, right? So for example, if we have element X, okay, a generic element, let's say that element X has two isotopes, 1 and 2, and they're both 50% abundant. So what that means is, if I went and looked for element X, and I randomly sampled element X, and I could pick up those atoms, okay, and I could count each one of those. Half of them, 50% of them, would be isotope 1, which has a mass of 50 AMUs, and the other 50% would be isotope 2, which is heavier than isotope 1, right? So if you think of a seesaw, since it's 50-50, we can simply add up 60 and 50 and divide by 2, right? So that would be 60 plus 50 would be 110 AMUs divided by 2. And look at that, we meet perfectly in the middle, okay, of the two atomic masses. But you can't do that all the time because some isotopes are not always 50-50. In fact, most are not 50-50, and some have 3, 4, even more isotopes. So this is where we use the weighted average. For example, all right, how can we calculate that last problem? How can we use numbers? So the average atomic mass, which we said was 55 AMUs. The way we get that is the average atomic mass is going to be equal to the abundance of isotope A times its mass. So in the last example, isotope 1 was 50% abundant, and its mass was 50 AMU. Okay. We're going to take that product and add it to isotope, it's a typo, isotope 2's abundance, which was also 50% or 0.50 as a decimal, times its mass, which in the last case was 60. Right? And we come out to 55 AMUs. This is simple because it's 50-50. We can simply take the average. But what if it's not always 50-50? In most cases, it's not. Right? For example, if we calculate element A, I'd like you to pause the film, and I'd like you to find what is the average atomic mass of element A. So at this time, pause the tape, and we'll go over the answer. Okay, by this point, hopefully you've solved for the average atomic mass. I'm going to peek back here. I'm going to cheat, and you should have gotten an answer of 70.6. 70.6 AMUs. I'm checking myself here. Right? So let's take a look at this. Isotope 1 is the most abundant, 90%. Isotope 2 is 10% abundant. So in this case, we're not 50-50. We're not 50-50. And if you think about it, think about which way the average should tilt. Should it go more towards 70 AMUs on average? Or should it lean to 76? Looking at these numbers, you're probably telling yourself, the average should be very darn close to 70 because 90% of element A is in the form of isotope 1. So here's the answer key to this. Here's what I did. Okay? To find the average atomic mass of element A, I took 90%, which is 0.90, and I multiplied that by what isotope 1's mass was, which was 70. So 0.9 times 70 got me 63 AMUs. So that's the mass that isotope 1 contributes to the average. Then I added that to the abundance of isotope 2, which was 10%, or 0.10, times its mass of 76. 0.1 times 76 is 7.6, so I add these terms up, and I get an average atomic mass for element A of 70.6. Once again, look how close this average is to our most abundant isotope. Okay? And you're going to see that on the periodic table. The average atomic mass is always skewed to the more common isotope. Okay? So far, so good, hopefully. Okay, here's our last example. We have 3 isotopes. Here we have 3 isotopes. Element B has 3 isotopes, 1, 2, and 3. I'd like you to take a moment and look at the abundances, okay? 1%, 15%, we don't know what that last percentage is, but I will tell you there's only 3 isotopes for element B. And here are their masses here. Okay? So at this moment, once again, try this. Pause the tape now and calculate the average atomic mass. Okay, we're back, and we're going to take a look at this. So first off, the first thing I can fill in is say, well, the average atomic mass is going to be equal to the abundance of isotope 1. So 1% as a decimal is 0.01 times its average mass, its atomic mass, which is 22 AMUs. Okay? And I'm going to add that to isotope 2. So 15% abundant is 0.15, and I'm going to multiply that by 26 AMU. I'm going to squeeze that in here. 26 AMUs. And I'm going to add that to the abundance of isotope 3. Now, we don't know the abundance, but we can figure it out. If there's only 3 isotopes, this is 1%, 15, that's 16%. The remainder has to be 84%. Right, so 84% of isotope 3 is 0.84 times isotope 3's mass, 19 AMU. And now this becomes a real easy calculation, right? So we have 0.01 times 22 AMUs, I get 0.22 AMUs, plus 0.15 times 26.00 gets me 3.9 AMUs. Finally, we add in that third isotope, 84%, 0.84 times its mass, 19 AMU. We get 15.96 AMUs. All right, so let's simply add these up. I get 15.96 plus 3.9 plus 0.22, and I get an average atomic mass of all the isotopes of element B to come out to 20.08 AMUs. Now, does that make sense? Is the average skewed towards the more common isotope? It is. 20 is very close to 19. Okay? Hopefully you'll learn something from this flip session, and I'll see you next time.